13. Thanks for joining again. I would like to continue on talking about models and signals of dark matter. What I'd like to do, so we started by discussing a variety of different scenarios. To now I want to move on to sort of more modern models and the anomalies that are motivating people to think about dark matter these days. So I'm going to go back and forth a bit more slidey in this talk, but still go to some of the notes. We discussed already the glossary of dark matter and did most of a canonical WIMP. I'm going to talk about portals of dark matter, in particular the vector portal and models of dark matter that come with the vector portal, and then talk about the various anomalies and how you can explain some of them with ongoing models. So let's just remind ourselves what we were thinking about in the context of a canonical WIMP. So I was describing a canonical WIMP as being this something like a heavy Higgsino or a fourth generation Dirac neutrino. And if you take a model like that, if you imagine that you want to think about dark matter, which is a hypercharged 1/2 SU2 doublet, then its dominant annihilation process is what we've got here, but namely that it annihilates into these W bosons with a cross section which is easily calculable, and gives you this result, which is approximate but fairly good, where you get the appropriate relic abundance for a dark matter particle that has a mass of around TeV. Once you have a model like that, you can start thinking about the actual signals of it. And this is going to give us the intuition that we need to think about the models that are going to come later, because basically the phenomenology that you see occur with this very, very conventional WIMP is actually something that will show up again and again. So as I said, one of the canonical signals that we like to think about is the direct detection signal. So in that, we imagine that you've got some sort of nucleus here made out of various nucleons. Dark matter comes in, scatters through some sort of interaction. The nucleus recoils, and you look for that nuclear recoil. You can calculate this rate. The differential rate is a function of energy. And it's fairly straightforward calculation involving the density of dark matter, how many atoms you have in your target, the couplings of the WIMP to protons and neutrons, and this velocity integral. So when you do that for this canonical WIMP, you get a cross-section which is around, per nucleon, which is around 2 × 10⁻39 centimeters squared. So remember, this is not the cross-section off of the entire nucleus, because different experiments have different targets with different numbers of nucleons. So this is a cross-section on an individual nucleon. And so you can ask yourself what that looks like. And so here is an example of what current limits look like. And this is sort of the canonical plot. You probably have seen something like this before, but if you have not, you have the WIMP mass along the x-axis, and this cross-section per nucleon that I was just describing on the y-axis. And the strongest limits in this sort of parameter space are currently from xenon 1 ton, which is a large liquid xenon detector. And everything up here is excluded. And you can see the parameter space they're reaching is down here at about 10⁻45 centimeters squared, which puts the actual signal that we're talking about way, way, way up here, not even on this slide. So this is just to say that this kind of a model, this SU2 doublet, is not only excluded, it was actually excluded about 20 years ago by these sorts of experiments. So what's the purpose then of talking about it? Well, the purpose of talking about this is because if you think about what the interactions are, it's a little bit more subtle. So ordinarily, you have a Dirac fermion has a mass matrix, an off-diagonal mass matrix that marries the left and right-handed components. And it's not unreasonable to consider what happens to that model if you put some sort of diagonal Majorana mass in there as well. If you do that, what happens is that the Dirac fermion you have splits into 2 pseudo-Dirac states. with masses which were what you started with, but shifted up and down by an amount. Sorry, that's minus. By an amount of the splitting that we've just added. So if you add a Majorana mass delta, you're going to take those two Majorana states that are part of the direct fermion and split them up by a small amount. Now, if you think about the interaction that you have to, say, a weak gauge boson, it's proportional to the Fermi constant. Sorry. And then you have some sort of vector current interaction that couples your dark matter particle to a nucleon that's mediated by the gauge boson. But this here is only non-zero in the case that you have a Dirac fermion. If you have a Majorana fermion, say psi1 gamma mu psi1, this vanishes identically. And that's pretty obvious why that should be. That's suppressed because vector currents are coupling to conserved charges. Majorana fermions don't have any conserved charges, so they can't couple to a vector current. So, but we know we started with a vector current, so what does it look like? Well, the vector current has now changed into one which is off diagonal. So you have a psi1, psi2 interaction. So you have transitions that mediate processes that take you from this psi1 state up to the psi2 state and back down. However, if you take that splitting and you make that splitting sufficiently large that you cannot access this higher state, then you can turn that interaction off entirely, and you won't have any scattering cross-section, which is mediated by the vector interaction any longer. And you've now taken a model which was very, 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 very dead and turned it into one which is maybe only sort of dead or maybe still alive, depending on what you actually do with it. A second. I just realized I'm supposed to turn that off. There, turned it off. You turned it into a model that is still possibly alive. And it's a fairly moderate, minor modification of the model to do this. So, so that's the background. That's sort of a canonical model. I think it's a very useful one to think about because it's a baseline. It's one that we think about all the time. It tells us how to iterate through the process of thinking about models, where you take the things that you know about the model, calculate the relic abundance. That gives you some quantities that you know about the model. You can then compare that to observational data and go from there. But it also shows you that a bit of clever model building can take a model which looks like it's in a lot of trouble and turn it into one that's not. So let me go on and talk about models that are a bit newer. So these I'm going to loosely refer to as portal models of dark matter. So what do I mean by portal models? There's a basic question when you think about dark matter, if you want to discover it, which is how does this dark matter actually talk to us? And so you can imagine that there's the standard model here, and there's a dark sector over here. And you can ask, what is going to be this communication? Now, the situation we just talked about was a situation where the dark matter was actually charged under SU2. But if we step away from that and we imagine the dark matter is not charged under SU2 cross U1 or SU3, it's not charged under any of the gauge groups, then you have to ask the question, well, how is it going to talk to us? Well, if dark matter doesn't carry any gauge charges, then we have to think about gauge invariant operators. And there are 3 dimension 4 gauge singlet operators in the standard model. And these are what people typically refer to as the renormalizable portals of the standard model. So you can imagine you might have a singlet scalar field S, and you can write down S squared H dagger H, where H is the standard model Higgs field. You can take the standard model left-handed lepton and contract it with the Higgs boson, and that makes a gauge singlet LH and marry it off to a fermion N. So this is called the Higgs portal. This is called the neutrino portal. And then lastly, you can imagine that you take the standard model hypercharge or low energies electromagnetism field strength tensor, and you marry it off against some sort of dark U1 FD. And this causes a mixing between the standard model electromagnetism and some dark sector. And this is referred to as the vector portal. And these three portals give you the opportunity to talk about a sector which has absolutely no gauge charges of the standard model, but talks to us in some sort of renormalizable way. And of course, the details are in the models. You can't just write these things down and understand what's really going to happen. So what I'm going to do is I'm going to focus on this one and think about it. And I can talk about other ones on another time. But there's so much richness in any one of these that you really need to focus. So let's imagine for a second that we're talking about a situation where we have a massive dark photon. That's the parlance people like to use to call these things dark photons. Sorry, I'm just making sure that I have my chat available when I need it. People refer to these things as dark photons. And so what we're going to imagine is that you start with this kinetic mixing term that mixes the standard model F mu nu with the dark F mu nu. And then, of course, you have the standard kinetic terms of these different sectors, as well as a mass for the dark photon. Now, it's important that we're considering a situation right now with a mass. You can consider situations without a mass, and I'll talk about those in a second. But if you start about thinking about dark sectors where the dark photon has a mass, it's important because that automatically chooses a basis. Because what you'd like to do is you'd like to take this kinetic mixing term here and get rid of it. And the way you can actually get rid of that is by making a field redefinition of one of your gauge fields. But because you have this mass term here, you don't really want to do a redefinition where you replace a dark with something, because that's going to take a nice diagonal mass term and turn it into something which is not diagonal. So what you do is you take the standard model gauge field and you replace that with a linear combination of the standard model and epsilon times the dark gauge boson. And when you do that, you can, when you expand that out, you can cancel off the kinetic mixing term, and you're left with two gauge bosons, both with diagonal kinetic terms and with a diagonal mass term. The cost, though, is that you say, if you imagine, for instance, the interaction of a standard model fermion, say an electron, with this with the ordinary photon, that then gets replaced by the same coupling to the standard model photon, plus some new coupling to the dark photon. So the upshot of this is all standard model particles pick up interactions to the new dark photon. Now, it doesn't work the other way. Dark sector particles do not pick up interactions to ordinary electromagnetism because the mass of the dark photon is actually chosen a basis. And what we ultimately call the photon is, almost by definition, the massless state. That's what mediates long-range electromagnetic interactions. So whatever that massless state is, that's what we call the photon. And the dark sector does not talk to that massless state. The question came up in the neutrino portal. Could I repeat what is the dark particle? Well, this N here is a dark particle, if you will, in the sense that it is not charged under anything. But whether or not that is actually the dark matter really depends on the models in question. And I'm happy to talk in nauseating detail about that later. If the dark matter sector has some gauge symmetry, is mass term allowed for the dark photon? Of course, not tree level if you have an intact gauge symmetry, but it's pretty easy to put in a mass term. You can imagine some Stueckelberg mechanism, or you can imagine that there is some additional Higgs boson that's breaking that gauge sector. And you can consider a case where there is no Higgs boson and you have two massless fields, and that becomes what's referred to as millicharged dark matter, which has qualitatively different phenomenology and searches. So for the moment, though, I want to focus on this situation where we have a mass term for the dark gauge boson, and all standard model particles pick up some very tiny interaction. And the idea that here is this epsilon term is something like 10⁻³ or smaller. to make consistent with various experiments. If that's true, now we have two sort of limiting cases where you imagine that you also have a dark matter particle. So you imagine that this dark photon is part of some bigger dark sector where there are dark matter fields as well. And you can consider situations where the dark gauge boson is heavier than the dark matter and situations where the dark matter is heavier than the dark gauge boson. In this case here, you have a possibility of dark matter annihilating into these A darks, which are also called A primes very often. And then that A prime can stay in equilibrium with the standard model through something like a Compton scattering process with, say, electrons or any charged particles in the standard model. In this kind of a scenario, it's it sort of breaks a lot of your intuitions about WIMPs because the dark matter doesn't actually have any real conversation with the standard model. It's really just talking to this dark photon, and the whole dark sector only has connections to the standard model. In that case, really your searches for the dark photon, these are your best experimental searches here, and looking for the dark matter is much harder. More recently, I think the attention of these sorts of dark sector models and these vector portal models has really changed focus though on the situations where the dark matter is lighter than the dark photon. And then you have processes like this that mediate the annihilation of dark matter in the early universe. And people like to parameterize these models with this parameter y, which is epsilon times alpha dark times m chi over m dark photon to the fourth power. It's a dimensionless parameter that sort of shows up and allows you to compare various different constraints because they often can be written in terms of this parameter y. In this case, the annihilation cross-section is proportional to epsilon squared alpha dark alpha electromagnetism times 1 over ma to the fourth times m chi squared. But if you take your intuition and you say, well, if I want to have a thermal relic, this overall cross-section here should have a scale which is something like 1 over TeV squared. But what's interesting is that you're now talking about a situation where you have this additional small parameter in the problem, namely this epsilon parameter, which suppresses the overall process. And that means that the scales of the problem can be much lighter and still get the appropriate relic abundance. Put it simply, this allows you to have light dark matter, which people really think of light as sort of like GeV and sub-GeV dark matter, which annihilates into electrons and light fermions. If that's true, the direct detection is really, before I told you that you think about this annihilation and then you can kind of like imagine that, you know, this direction is annihilation and then this direction is a collider search and this direction is some direct detection cross-section. But then I said it's all kind of PR because you never know if these things are related. In this model, these things actually are very, very much related. The scattering cross-section is really just rotating that diagram. And you can put an electron here or a nucleon, depending on the mass in question. And you get a scattering cross-section, which has the same parametric form with some kinematical corrections, which goes like this y parameter over m chi squared. So you can think about the direct detection signals as being very, very, very tightly connected to the signals that we've already been talking about. But the problem of these models is that if you allow this annihilation process here, so standard model or chi going into E plus E minus, it's going to have trouble with the CMB. So as you just heard from Yassine, energy injection during recombination is a big problem. And if you imagine what the overall injection rate goes like, well, the energy density here, remember for a thermal relic, rho goes like 1 over sigma. The number density goes like rho over mass. So if you're imagining dark matter is annihilating with itself, the overall rate is proportional to the number density squared, which goes like rho squared over mass squared. But then the energy that gets injected into the plasma is then take the overall process and multiply by m. So this whole thing goes like 1 over m, which means basically as you go to lower and lower masses, you're actually injecting more and more energy into the CMB during recombination. Yes, each individual annihilation has lower energy that it's contributing, but because there are so many more pairs, you're actually getting more energy overall. So Yassine did not show this, but these are sort of basically the limits that people talk about from Planck. This whole region up here is what's excluded. And these are different reaches of different possible experiments. On the x-axis here is the mass of the dark matter. On the y-axis here is the overall annihilation cross-section. This dashed line is some sort of canonical dark matter cross-section. But that's assuming that all the energy gets efficiently injected into the plasma. In reality, you have energy which can go into neutrinos, so it might get suppressed by a factor of a few. And so this is sort of a band of plausible models that you see. But the upshot of it is that basically, once you get down below about 10 GeV or so, if dark matter is annihilating with any sort of efficiency into electromagnetic energy, it's just totally dead from the CMB. That those light particles, if they're thermal and are continuing to annihilate during recombination, would have just been completely ruled out. So you can then ask the question, all right, if I really don't like this, if I want to keep thinking about light dark matter, well, how am I going to do that? Basically, it comes down to this fact that you need to not have dark matter annihilating during recombination. That's the problem. If it is, then there's really nothing you can do about it. So how do you turn off the annihilation? There's basically two options that people think about. One option is that if dark matter is a complex scalar, then the overall annihilation rate is P wave suppressed. Wow. Is there something going on in the background? Is it this sound? That's my chair.
Oh, okay.
That's my chair. I'll try not to move around so much. I just gesture and it causes my chair to make noise. I'll try to sit still. So if dark matter is a complex scalar, then the overall process becomes P wave suppressed. And if it's P wave suppressed, then even if in the early universe, when it froze out, the cross section was large, by the time you get to recombination, this thing is so slow and so cold that the annihilation can effectively have turned off and be irrelevant. The other possibility is that instead of having a Dirac fermion, you turn it into a pseudo Dirac fermion. So this is a model trick, which is not at all unreasonable. If you don't have any conserved quantum number, not something, if that quantum number is approximately broken, it's natural to imagine that those Majorana states should be split from each other. But if they are split from each other, then this annihilation process, well, just as in the case of the Dirac fermion model of dark matter, the Dirac SU2 doublet model of dark matter, if you imagine that this is a pseudo Dirac particle, that dark matter particle will be split into chi1 and chi2. And if you look at what the annihilation rate is, or the annihilation process, it's chi2, chi1 into E plus E minus. And so if the mass of chi2 is big-ish enough, bigger than the mass of chi1, then by the time you get down to recombination, you can have depleted enough of the chi2s that this annihilation process won't happen, which is that if there's a Boltzmann suppression of chi2 versus chi1, then you'll end up with just chi1s, and this process will have turned off by the time recombination happens, and you're safe again. Pseudo is in the sense if it's a true Dirac particle, then the two Majorana states of it must be degenerate. Because these things are not exactly degenerate, you can't really think of this as a single fermion. It's two separate mass eigenstates, but they're close enough that you call it a pseudo Dirac. If you split them by a lot, by order 1, then you would no longer even call it pseudo Dirac. Then you would just have two Majorana fermions. So these are basically the two options that one can consider for solving these problems. Oops. So if we're going to think about these dark matter models, which annihilate through these dark photons, then we can ask questions like, well, okay, what are the limits on dark photons? What are the limits on dark matter that annihilates like this? The first place to look is in the limits on dark photons. Usually the assumptions are that dark photons either decay into E plus E minus, because there's nothing lighter than that this particle can decay into, or it can decay into dark matter, and the limits are different for different scenarios. If the dark photon can decay into E plus E minus, this is what the limits kind of look like. There are a huge number of experiments with a wide range of different possibilities. Down here, these are beam dump experiments. These are generally accelerator experiments. This is this green band is a favored region to explain G minus 2. And then you've got these unshaded regions, which are future experiments, which are going to look for this. But basically, you can see that right now, the limits are kind of around here, 10 to the minus 6, which is kind of saying that once you get down below the level of soft photon emission of any electromagnetic process, your ability to control and not miss a light photon or low energy photon is weak enough that you basically can't exclude these things. So that's sort of the range which is currently allowed, where epsilon is less than about 10 to the minus 3, and masses that are sort of in this range. And if the dark photon could decay into dark matter, so it's an invisible decay, the limits get even weaker. So let's think about the limits on dark photon, dark matter. You can think about the elastic and the pseudo-Dirac fermion scenarios separately. And you have this Y parameter here that I was talking about before, which is just a way of parameterizing the dark coupling constant and the kinetic mixing and the mass of the dark photon to the dark matter, and combining it into sort of like one relevant parameter. So you have that versus the dark matter mass. And you have here this line here for the complex scalar and this line here for the pseudo-Dirac fermion versus all of these limits out there. There are future experiments here, LDMX and Bell too, which should probe a lot of this region in the future. Excitingly, it's not just these accelerator experiments that are going to look for dark photons in the future. You can also look for it in direct detection. So if you have the scalar case, so that's not the pseudo-Dirac case, but the scalar case, then it can scatter elastically, and you can look at it scattering. If it's too light to actually scatter off of a nucleon and deposit energy that you can see, but even in these sort of like low mass ranges of 10 to 100 MeV, dark matter can scatter off of electrons and deposit energy. And there's an exciting proposal to do an experiment called Sensei, which is looking for specifically this. Xenon 1 ton, which we'll talk about later, also can look at these low energy electron recoils as well. So the upshot of all of this is that vector portal dark matter is a really exciting paradigm, because it allows you to consider the possibility of very light dark matter, so down to an MeV or so, and yet to have appreciable connections and signals to the standard model. That said, any light thermal particle that is annihilating during recombination has a problem, and so you need to imagine this is either a scalar or a pseudo-Dirac particle to avoid those problems. And this is something I want to just emphasize now, because we're going to be coming back to it, which is that these models of light fermion dark matter often seem to need these excited states. So if you think that it's more natural for you to have a light fermion than to have a light scalar, because light scalar would come with whatever structure it needs to keep it light, its own hierarchy problem, then these pseudo-Dirac fermions seem to be a fairly common presence in something people think about in these models. So let me stop and see if there are any additional questions to take at this moment. I've been trying to answer them as I go along.
Yeah, so I think most of them you have answered, and I don't see any more questions on the YouTube
All right.
channel.
All right.
Yeah.
All right, well, let's move on to a discussion of anomalies. So by anomalies, I mean putative signals in the data that might be indications of something interesting or real. And it's always, there's different people with different attitudes about whether or not you should think about anomalies or why you should think about anomalies. And so I'm going to give you my take, and that's just one person's take, but I'll give it to you because I'm here. So why should we think about anomalies? And of course, the easiest answer is, well, they could be real. Yeah. Somewhere between definitive proof of something and having no idea about something, it usually goes through some period of uncertainty. We saw that with the cosmological constant. We saw that with neutrino mass, where there was a period where things were not totally cut and dry, but you could either think about them or you could not think about them and wait until everything was clear. Whether you want to wait is up to you. But the reality is that most anomalies ultimately go away. And if you want to think about them, you need to be straight with yourself about that fact. But I think they're still extremely valuable because they give you a very concrete, observable target to try to address. Something that gets you to question your assumptions. Why did I assume that? Why did I go to that region of parameter space? What was, driving me to do that? And they give you a quantitative target to hit so that you really can have a discussion about something. Sometimes that quantitative target can lead you astray, but it's something to focus your energy on to see if you can address. So in my mind, anomalies are a very, very efficient driver of thinking about new models and have been a real benefit for thinking about dark matter and expanding our idea. So I'm going to talk very quickly about a few anomalies with most of my time spent on some particular solutions to the xenon 1-ton electron excess. But let me take you through some of these anomalies. I'll take you through an anomaly of small scale structure, DAMA, which is a classic. I'm not going to spend any time on galactic center today for the sake of time. 3.5 keV excess and xenon 1-ton. Yes, by excited state, I mean the higher mass state of the pseudo-direct fermion. So let's think about the centers of dark matter halos. So if you go to the centers of dark matter halos, you can think about the density of dark matter in those halos as a function of radius. And that was a terrible curve. N-body simulations tell you that the density of dark matter should rise quite rapidly as you move towards the center. And you usually parameterize in the interior region the slope of it by some parameter alpha that tells you how steeply it's growing. And most models would suggest that it should have a cusp that goes something like 1/r or thereabouts. That's sort of what you see in dark matter only simulations. Let me stress that I'm talking about dark matter only simulations at the moment. But if you look at the data, so you can go out and you can measure the kinematical properties of dwarf galaxies. What you see is that, so this is a combination of studies from O et al. In 2015. And what they find is that the profile in the inner regions of these galaxies seems to be much more clustered around an inner slope of 0 or power of 0, which is to say a flat core, versus this alpha of -1, which would have been the cuspy profile. So there's a question, which is why, instead of this cusp, which ubiquitously shows up in N-body simulations of dark matter, do you have something which is much flatter? There's another question that comes up, which is that if you actually look at different dark matter halos that have the same ultimate mass enclosed in them, which is this plot on the right here, you can have a lot of differences in the interior region. In this interior region here, so which is called the diversity of halos, and the problem of the diversity of halos, that even though they have the same mass, their interior properties are very, very different from each other. And so one possibility could be that if dark matter has interactions, has self-interactions, then you have the possibility of excuse me, energy transport within the system, and that energy transport can flatten the core and change the inner workings of it. Now, I think that a lot of people would say, well, baryonic effects, if you take into account baryons, can also do this. And I'm not really going to get into that discussion because that's really a question for specialists. The point here is that these changes in the inner properties of these halos is motivating us to think about other possibilities of dark matter. So this goes by the phrase, the name of SIDM, or self-interacting dark matter. And typically, if you kind of like ballpark estimate what you actually want to have happen here, you want this thing to have about one scattering over the age of the universe. If you have many, many more scatters than one over the age of the universe, then the energy transport is so bad that this doesn't look like cold collisionless dark matter anymore. And we know to a pretty good approximation, it's cold collisionless dark matter. So much, much more than one is bad. On the other hand, much, much less than one over the age of the universe is you're just back to CDM. So you want something around one per age of the universe. And you can kind of go through and, ballpark it and just imagine, for instance, the local density of about 3 GeV per cubic centimeter. Ask, well, if I imagine that dark matter has some scattering cross-section, it's moving at a velocity of about 200 kilometers per second. It's been doing that for the age of the universe. What do you end up with? Then you end up with something which is, around 100 to 1,000 grams per cubic, centimeter square per gram, which is actually much bigger than you really need, because we are, of course, not in the center of a dwarf galaxy where the densities are higher. So if you move to those things, typically the number that people will talk about, and this is sort of the canonical number you'll hear people talk about, is about a centimeter squared per gram, which is a funny unit. Most particle physicists don't think in terms of centimeters squared per gram, but that's sort of how people quote it. If you convert this into natural units, that's something like inverse 100 MeV squared. So this is a very, very strong, if you imagine that this is being characterized by a single scale, this is a very strongly interacting particle. And people might have worried about whether that's in conflict with anything. But really, that's not anything except for telling you that if you have a particle whose mass scale is characterized by sort of the MeV scale, then it would very, very naturally have these sort of centimeter squared per gram self-interactions. And so one of the reasons that SIDM is getting a lot of interest and attention at the moment is because not only do we have these observations that are telling us that we have deviations from these n-body simulations, but we also find a natural home in these MEV or sub-GeV dark matter models that SIDM can be quite present. Although I'm not going to talk about it here, let me just also mention that there is an exercise that I'm going to lead to the reader, which is, instead of we talked about before, we talked about a 2-to-2 process when we talked about thermal freeze out. You can also consider a 3-to-2 process. Yes, 3 GeV per cubic centimeter is about the value of dark matter energy density roughly here, we think. If you think about a 3-to-2 process, then instead of n sigma v equal to h, which is what you would have had for the 2-to-2, you can think about n squared sigma v equal to h, which is the 3-to-2 process. And if you follow your nose, you end up with a cross-section which is around 100 MeV squared. So this was referred to by these people as the SINP miracle. I don't know if it's a miracle or not, like the WIMP miracle, but the idea is that if you, instead of thinking about a 3-to-2 process, you consider a 2-to-2 process, you consider a 3-to-2 process, you also find a natural home for these sorts of dark matter models that have these strong interactions. Like I said, I'm not going to go into it. I just wanted to mention that that this is a very natural consequence of these dark vector portal models. It's certainly an open question whether the cores that we see are from dark matter or baryonic effects. But I think it's important to emphasize that there's certainly room for dark matter interaction. And I think we all recognize that it's really not a question of if there's some point where it's not cold collisionless dark matter, but when it's no longer cold collisionless dark matter. There are some interactions somewhere of something. And it's a question of whether you find it, whether it has an interesting signal. And so this is one possibility. So moving on from that, let me consider a line at 3.5 keV. So a few years ago, in 2014, there were two papers, essentially simultaneous, that claim to look and see evidence for an X-ray line at around 3.5 keV. And this is now referred to as a 3.5 keV line. Originally, it came in different systems using different experiments. So you had both Chandra and XMM Newton as experiments that were looking for these things. These teams looked at combinations of clusters, Perseus cluster individually, M31, and others, and found that this 3.5 keV line was present in a number of those systems. Now, these are the original data here. I might just emphasize that it's hard to see, but if you blow it up, you can see these small excesses here, here, here. And how convincing you find is, up to you. That's of course the original. This passes what I like to refer to as the Toro test, which was introduced to me by Natalia Toro at SLAC, which is, if you turn the plot upside down, do you find it as convincing as you would have the right side up or not? And if you do find it more convincing the correct way, then that passes the test. And I do think that these plots are more convincing as an evidence for an excess when you hold them the right way. So I say it passes the Toro test. So what could this be, assuming that it's physics beyond the standard model? The sort of canonical thing that people like to think of is the decay. And the idea is that you have some particle, a particle whose mass is, say, around 7 keV, which then decays into some massless particle plus a photon, and that photon carries away half of the energy. By far, the most commonly discussed scenario is the sterile neutrino. So that is a 7 keV sterile neutrino, which decays through its mixing with the standard model neutrino radiatively through this loop into a massless neutrino and a photon. And I want to give credit, so people like Raghavan, George Fuller, really thought about these things for a long time before there was any data. And for a long time, we're saying, hey, there should be an X-ray signal of these things if they're real. And as I mentioned yesterday, if you think about sterile neutrino dark matter, the constraints on it are if it's too light, then it destroys structure. If it's too heavy, you get an X-ray signal. So you're already living in a region where you kind of are starting to expect an X-ray signal. So, I think that although there are a lot of tensions in the current data set, it's pretty interesting that they did really predict this. That doesn't mean it's right, but they did say we should look here, and part of the reason we're looking here is that. But there have been a lot of studies since then, and not all of them see evidence for this line. People look at dwarf galaxies. People look at regions of blank sky. People look at other clusters. People look at different regions of M31. And sometimes they see what looks like an excess 3.5 keV, and sometimes people don't. There are arguments whether you're just seeing some sort of standard atomic excitation that you're misinterpreting because of how it's distorting your interpretation of the spectrum. Those are all sort of inside baseball discussions. So I just want to take a look at this plot. All these colored regions here are different positive signals. So Perseus, looking at a stack of clusters, looking at M31. These are all different regions that have claimed to see evidence for this line. And you'll note that it's put in terms of this parameter of sine squared 2 theta, the effective weak mixing angle of the effective mixing angle of a sterile neutrino. And this is sort of spanning about an order of magnitude in overall rate. So these are not totally right on top of each other, but they're pretty close. Then you've got these limits from various experiments. There was the really tragic Hitomi satellite that was going to definitively answer this, but then broke apart shortly after its launch while it was just beginning to operate. And then there's this recent paper, which is blank sky observations, which does not see it. And at this point, there's certainly tension between the positive observations and these at least blank sky observations, but maybe it's not totally enough to say it's dead, dead, dead. but it's certainly enough tension to say maybe you should think about other things. So So one idea is that instead of taking this 3.5 keV scale as specifying the dark matter particle mass or telling you something about the dark matter particle mass scale, it can instead be telling you something about, for instance, one of these splitting scales, and something you could do is think about splitting models. So for instance, you can consider a situation where dark matter scatters off of itself into an excited state. That excited state then propagates through the universe for some period of time, and then de-excites, emitting a photon. And then you identify this thing here as the 3.5 keV photon. So there's some splitting, which is 3.5 keV between the excited state of a pseudo-direct fermion and the ground state. They scatter it. And when it de-excites through, for instance, a dipole operator, you get the observable signal. And the reason why this is sort of an interesting model is because, for instance, the scattering rate is proportional to dark matter squared, whereas the decay signal is just proportional to the amount of dark matter. So they'll have different morphological features. This one cares about being in high velocity environments where you can actually excite, as opposed to low velocity environments where you might not have the kinetic energy to excite. So not to say that this is some panacea, but it gives you a different morphology, it gives you different types of signals, and it's my understanding, at least at this moment, this model is still okay. There are other possibilities people considered, so you can imagine dark matter scatterings that get you into the state. You can imagine dark matter baryon scatterings that get you up into the excited state. There are possibilities where photons themselves can excite the dark matter through this dipole transition, and then it de-excites, giving you this signal. In all these cases, you need fairly large cross sections. In the dark matter case, you're approaching, but not all the way at the strongly interacting region. But again, I think it's interesting that a model like this is something which you already are kind of seeing in this, light dark matter model scenario. Okay, let's move on. So let's move on to DAMA. DAMA is the sort of like granddaddy of dark matter anomalies. It's been around forever. I don't have anything concrete to say about it, except to point out one model you may not know about. It's a sodium iodide experiment. It looks for scintillation signals, so it can't tell you the difference between a nuclear recoil and an electric recoil, but it looks for a modulation. So if here's the sun, and we're in the Earth going around the sun, and if you imagine the sun is moving this way, there's some times of the year where our motion takes us with the Earth, with the sun, and sometimes we're moving against the sun's motion, which means that the flux of dark matter particles is modulating on an annual basis, and you would expect to see a higher rate of dark matter scatterings in the summer and a lower rate of dark matter scatterings in the winter. They've been running for a very long time, 20 years. They upgraded their experiment to go down to lower energies a few years ago, and they see, even in this low energy regime, this consistent modulation. It's roughly 1% or a couple percent of their overall count rate. And it passes various other constraints that you might worry about as well. Problems. You would have expected other experiments to see this, and they don't. And the other thing, which is kind of strange, and I think is an underappreciated when thinking about DAMA, is that, yes, we talk about 1% of the signal or 2% of the signal being modulated, but 90% of the signal there is well understood to be of radioactive decay origin, that it should be unmodulated. So if you believe that you're really not playing with that 90%, you're playing with that 10%, this is not a 1% or a 2% modulation, this is more like a 10, 20, or 30% modulation. So whatever signal is modulating is something which needs to be modulating at a really huge level. And that's hard to do. And that's hard to do whether you're talking about a background or a signal. That's why this model is really so, or this anomaly is so hard to really explain, because it's hard to get that large scale modulation of whatever it is that you're seeing modulate go up and down by 20, 30% over the course of a year. However, I want to point out a model which is a really clever idea. It definitely falls into the category of I really wish that I had thought of this myself, by Felstein, Graham, and Rajendran. And the idea is called luminous dark matter. So the idea is that you've got Earth, the dark matter particle comes into Earth, somewhere in the Earth scatters into the excited state, then that excited state goes into the DAMA detector and de-excites inside the DAMA detector, producing that photon. I think this is a cool idea. It explains why it hadn't been seen in other experiments. But at this point, this idea is ruled out. Okay, but this kind of an idea is still around as a model, even though it doesn't really explain them anymore. So lastly, let me go on to the xenon 1-ton anomaly, which is probably something which is driving a lot of interest at the moment. So xenon, even though it's primarily a nuclear recoil experiment, at least in its design, can also look for electron recoils. And so they can go to low energy and do that. So that's this here, the energy, and this is the events, the count rate. And they were doing a search for what they call the solar axion search, because in the sun, if you have axions, because of the keV temperatures in the core of the sun, you might produce axions at keV energies that could fly out of the sun, go into your detector, and give you energy deposited into the electrons, because axions are expected to talk pretty well to electrons. So that was the name of the search. And what they see here is this excess at low energy, which is around 50 events or so above their background. And one should always be skeptical of these sorts of rates that are going up at low energies, but that's what it is. Okay. So let's think of this as a model building challenge. The question is, how do you induce an electromagnetic signal in xenon that doesn't show up elsewhere? You need to have some particle which is going through your detector, which is giving you this energy. Kind of have two options. Either that's a primordial particle which is doing it, or that particle was produced somewhere, for instance, in the sun. And regardless of whether it's primordial or not, you need to make sure this is not overproduced in astrophysical environments, because this is clearly talking to electromagnetism somehow, because it's giving you an electromagnetic signal in this experiment. There are a lot of ideas, and when I upload my notes, I'm going to include not a complete, but certainly a list of possible models, which are not what I'm going to talk about here. But I want to continue going on in this idea of excited states, because it's an appealing one. The idea here is that you need the keV energy scale to appear in your problem somewhere, right? That could be an astrophysical energy scale. For instance, the solar interior gives you keV energy scale. It can be the mass of the particle, in the sense that it can be absorbing a boson with a mass of around keV, or it can be an energy difference, so a splitting between two particles. And that last option is something that you can then think about as possibly being an explanation, and you could imagine using an excited state of dark matter to explain it. So let's go back to where we were, consider an excited population of chi-star states, and ask how they might yield a signal. Well, there's basically two possibilities. You can imagine that you have chi-star that comes in and down scatters through a dark photon off of an electron. And in de-exciting, it gives that energy off to the electron. Or it can be de-excitation. So the chi-star can just emit a photon through the dipole operator, and that photon would then be absorbed by an electron, and you would read it out as basically the same signal. A downscattering process can be either a primordial population or some sort of locally produced population, whereas de-excitation can only be a local population. If you have dark matter de-exciting at this level in your detector, then it cannot be primordial. So let's ask this question about how many of these primordial excitations we expect to have. Well, it's fairly simple. You can just calculate the process. Chi-star can scatter off of each other into chi-chi. Comparing that to the standard annihilation cross-section, the standard annihilation cross-section is suppressed by an epsilon squared, which is, remember, 10 to the minus 6, 10 to the minus 7 or smaller. So this downscattering process can still be very, very efficient, even well after the annihilation process is turned off. So if you make this plot in terms of, say, the mass of the dark matter versus alpha dark, you can find primordial fractions as small as 10 to the minus 9. And you can find primordial fractions as large as 10 to the minus 2 or 10 to the minus 1. So there's a really large range of how much chi-star you expect to be left over from the early universe, assuming that it has a long lifetime. I want to take one moment as an aside to show that here are two plots of dark matter mass versus the dark coupling constant. Here we do delta of 3 keV, imagining that it's down scattering and producing a signal xenon. Here we do delta of 100 keV, which can have nothing to do with the xenon anomaly. And I really want to emphasize this fact, which is that some of the biggest mistakes I've made as a theorist are sticking too much to the parameters of the model that explain the anomaly. If you study an anomaly, run with it and go to parameter spaces outside that as well. You can ask whether this primordial dark matter can explain the xenon excess, and this sort of like medium blue range is about the range that you want to be in. This dark line here is the thermal relic abundance, and you see that consistent with existing beam dump experiments and CMB and accelerator experiments, it's very, very easy for these models to get the xenon rate that you want. What's interesting is that these excited states were always there and should always have been thought about. It's just that until the anomaly came along, people didn't put in the time to actually understand them. Let me skip ahead for purposes of time and talk about another possibility, though, which I think is also kind of cool, which is that instead of imagining you have primordial excited states that downscatter, perhaps you have excited states that are produced in the sun. Now, this was an idea that was talked about in the context of light, just ordinary light WIMPs without any excited states. And the idea is that you've got the sun, dark matter comes in, gets kicked out with the keV energy. And when it gets to the Earth, you now have a keV energy particle. The problem with that is it's pretty hard to get a very sizable kick inside the sun to a light dark matter particle, because you've got protons moving around and they don't really want to give a lot of their energy up because the kinematics are so different between the mass of the dark matter and the mass of the protons. But here, because the excited states, the kinematics are different, so it's actually very easy for dark matter to be kicked into this excited state, which then flies out of the sun, comes to Earth and de-excites. And this gives you another possible scenario to give you an interesting rate at the standard at the detector. So you can see they're qualitatively different. This red line here is the shape of just standard de-excitation, and this blue line is the shape of a solar reflected inelastic signal, which is somewhat broader and possibly gives a better fit to the data. Another thing which is kind of interesting, and it will be sort of the final qualitative thing that I want to observe, is that if the energy density, if the amount of dark matter that you're considering, if it's a thermal relic, the energy density of that dark matter goes like 1 over the annihilation cross-section. If all the cross-sections are related, then increasing the cross-section decreases the abundance that you have. However, in a scenario like this, the overall rate is equal to the scattering rate in sun times the scatter in the Earth. Since the scatter in the Earth goes something like the cross-section and the scatter in the sun goes something like the cross-section, but this whole thing is times rho, which goes like 1 over sigma. As you increase the cross-section, you have less dark matter, but the overall scattering rate still goes up because of that fact that you're scattering twice, both in the sun and in the Earth. So something like this could actually be sensitive to a very subdominant population of dark matter, because the subdominant populations of thermal dark matter actually have larger scattering cross-sections and thus larger signals. And it's something to always keep in mind that subdominant components of dark matter can actually very often have signals which are just as large as the dominant components of dark matter because of this counter scaling, that high cross-section things have less stuff and less stuff have higher cross-sections. So for the purposes of time, let me just conclude about this. I think that we're very much in a golden age of models right now. WIMP prospects for discovery have definitely gone down, not because there's anything wrong with WIMPs, but just because we've done so much work trying to find WIMPs that there's not so much space left to cover. So if there's not so much space left to cover, we need to move on and think about other things. And people are thinking about other models. In particular, these vector portal models are particularly interesting. The precise motivation is less clear, but the parameter space is incredibly broad. And if you think even beyond these vector portal models, there's a huge parameter space, model space out there to think about. And people are much more willing to think about it today than they were 20 years ago. And what's also exciting about that is that in contrast to the WIMP, where you really need to be a mega experiment to make progress, a lot of these models can be probed by experiments which are much smaller, much cheaper, and can still probe really interesting parameter space. And it's for this reason that I think these next 10 years are going to be incredibly exciting for new ideas of dark matter and new ideas of how to look for dark matter. So I'll stop there.
Okay, thanks a lot, Neil. There are a couple of questions which are left in the chat. So this one is from Subinoy. What would be a possible reason for the 3.5 keV signal to be present in some source and absent in some galaxy?
So, I mean, if you're really comparing apples to apples, I mean, if they're identical systems, then it should appear in identical systems, right? They have to be different. But the kind of general ideas are, for instance, that you have, for instance, higher velocities in, say, a cluster and lower velocities in a dwarf galaxy. So you can actually excite into the excited state. Things have enough energy to excite in the cluster, and they wouldn't have enough energy to excite in a dwarf galaxy. So you wouldn't get a signal in dwarfs, but you would get a signal in cluster. A lot of limits, for instance, from dwarfs come from looking at the outer regions of dwarfs. If your signal drops off like rho squared instead of rho, then where you thought that was going to be a strong limit because of decays, that's no longer a strong limit per scattering. Models where the dark matter scatters off baryons have sort of similar things, where the overall rate traces rho baryon cross rho dark matter as opposed to just the overall density of dark matter. So it's these sorts of differences, which, I mean, what I would say is that I just don't think they've been as fully explored. I mean, I talked to the people who did this blank sky observation. I'm like, look, you guys should try and do this and consider these other scenarios as well to find out whether they're really constrained. Yeah.
Yeah, so there's one more question actually, which I wanted to ask. So in the Xenon 1T experiment, do we understand what is the dip at like 17 keV or so?
So
that seems significant.
So there's this, yes. And this is something where people have argued that maybe this doesn't pass the Toro test. Maybe if I flip this plot upside down, you'll be just as convinced that there was an excess as you are with it this way. No, nobody knows what that is. It's pretty statistically significant, but it's not impossible. It can't really be a real signal because the energy resolution up at these energies should broaden it out to these neighboring bins. So you can't really have a real signal that lives just in one bin. It has to extend out somewhat if it were a real signal. So I don't think that there's really any, this is an ordinary background rate. So it's not like you can have particles that come in and then turn off the signal. So no, nobody really knows what that is. And some people have made a point of saying, look, the fact that this is there should make you very skeptical of this excess here. And maybe you should have been skeptical of this excess here because you should always be skeptical of things that are sort of like towards the bottom of the energy spectrum. On the other hand, like I said, anomalies serve multiple purposes. One of them is to try to actually explain it if it's really dark matter, and one of them is to get you to think about new things like this, say, solar excitation of dark matter, something that hadn't been thought about, or these primordial excitations giving discoverable signals in these electron signals. These are things that people had not thought about, and now we start thinking about because we're motivated to. So I think this is an interesting anomaly, may go away, but even if it does go away, it's prompted us to think about models again that we probably should have been thinking about.
Yeah, okay, great. I don't see any other questions. I guess you answered one other question from Subinoy. Has given so many still viable models. What is your personal take, intuition on dark sector? Where do you see dark matter search going on in the next few years? I guess that was partly addressed in your last slide, right?
Yeah, well, I mean, I think that it's, I mean, I would joke that it used to be that everybody had a model they wanted to propose, and now everybody has an experiment they want to propose. And, but that means that the legwork is that much more important. Tomer Volansky, I was at a conference and even commented that if you're not working on an experiment, you're not a theorist, which just turned my world upside down because I wasn't working on an experiment. but it just shows that, you know, there's an appetite for people to think about new searches. And if you have clever ideas of not just models, but how to look for them, there are people who are willing to talk about it, but you have to be really serious about it. You have to take the time to understand the experiments. But there are a lot of people out there, and there's a lot of funding opportunities out there for experimentalists who want to look at new approaches to look for dark matter.
Okay, thank you. Thanks a lot, Neal. And this was a wonderful talk. Thanks a lot for these lectures.
Thank you. I hope to be there in person before too long.
Sure. Yeah, let's hope that this pandemic just goes away after a few months. Thank you. Thanks a lot.
Thank you.
It's been great that you had to stay awake
It's been a pleasure.
for such a long time. Maybe I can try to unmute other participants so that they can applaud as well. And then we'll break for 20 minutes or so, and then begin at 12. Is that right, Subinoy?
Yes.
Yeah. So 12 o'clock for the next session.
Okay.
Thank you very much.
Thanks.